The first skill that I would like to see if students have had a chance to explore or have questions about when working with polar coordinates, which is what we're working with, is to be able to convert between the two to plot points and things like that. So let's try to see if people feel they were able to dip their toes into the water in that way. So I'm going to put up a couple of problems that I'm just going to make up and have you guys give them a try and then see if people have questions along the way. Okay, so let's do some examples. What is a polar coordinate point for 3, 3 in Cartesian coordinates? So the goal for this problem is for you to convert the point 3, 3 in Cartesian coordinates into a polar coordinate format. And then I'm going to also write an example to go the other way. But for the moment, go ahead and see if you could try to do this if you're already seeing the problem. So here's 1, 2, the Cartesian coordinates for following. Let's do this. Sorry, I'm just going to word this a little better. For the following points given in polar coordinates. Okay, so let's see if we can look at some of these problems together, see how you guys are feeling about them. So let's take a look at this first problem here. The goal was to take the point 3, 3 in Cartesian coordinates and convert that into a point in polar coordinates.
Wait, just to be clear, we're looking for the polar coordinates, right? That what's given is in Cartesian?
Correct. So what is a polar coordinate point for 3, 3 in Cartesian? So the 3, 3 is in Cartesian coordinates, and we want a polar coordinate point.
I got 3 square root of 2, and then theta would be pi over 4.
Okay. 3 times the square root of 2 and pi over 4. Okay.
I got the same thing.
Okay, thank you. All right, so if people are still thinking or trying to figure this out, let's put up for reference some of the equations that help us convert from Cartesian coordinates into polar or vice versa, since that's what these first two problems are about. So we're going to have, maybe put them up top here. Conversion equations. And I'm going to drop this down a bit. So we have x equals r cosine theta, and y equals r sine theta. And we have r squared equals x squared plus y squared, which you can square root both sides, of course. And we have that theta is the inverse tan of y over x. And so far, a couple students for this problem of converting 3, 3 in Cartesian coordinates into polar, a couple students got this. And so the goal for those who are still engaged is to try to figure out if you can convert the point 3, 3, where x is equal to 3 and y is equal to 3, into Cartesian coordinates where you need an r value and you need a theta value. Well, it looks like everybody who did it got the right answer. So that's great, but then that means it's not really anything for me to do. So that's the correct answer. So maybe then try working on the second problem. So let's just leave it at that. So try now, the point is to find the Cartesian coordinates for the following points that are given in polar coordinate form. And there's 4 to work on, and you can do this graphically or with conversion formulas or whatever you want. So try to see if you could come up with the 4 Cartesian coordinate versions of these points. Okay, Maxime's got that done already. So you have possible answers here.
Yeah, I just have to step aside real quick. So that's why I did them in advance.
Oh, no worries. And that way, if people get an answer, they can check it with the one that you got, see if they agree, or provide another possibility if not.
I agree.
Is that Parjit? You got these same answers?
Yes.
Thank you. Okay, you talking about the first one?
Yeah.
Okay. So what'd you get?
I got the opposite.
You got
I'm not sure.
-1, 0? Was that what you mean by opposite, or
Switched around.
0, 1?
Yeah.
Okay, thank you. So another possibility is 0, 1. And we'll try to see what the discrepancy might be after a few more people have tried it. For C, I got 3, 0 instead, so another reversed one. Okay, so let's take this work about converting from one to the other and talk about sort of some of the properties of working with polar coordinates a little bit, that you end up understanding and learning these things a little bit when you work with them for a while. You can just say it up front, but it's hard to understand it. So for example, one of the things I didn't get into in the video, because you want to kind of work with things for a little bit before you think about it, is some of the properties and symmetries of polar coordinates. So for example, we just noticed, again, let's say I have my primary line here. So this is where theta is equal to 0. And so what we noticed, if theta is equal to 0, then you have some point on what would have been the x-axis in Cartesian coordinates, or what still is the x-axis if you're considering it in Cartesian coordinates. Because if theta is equal to 0, you're on this line. And as we saw in our point at the 1, 1, so let's say I'm out here, and let's say that that's where 1 is, that if I have a point here, when I'm then in polar coordinates, we would be looking at an angle of 0, and then the r value, the distance from the origin, would be 1. So, but this is also 1, 0 in Cartesian coordinates. And you can imagine that if I instead made this a -1, well, then I would be, r would have a negative value, so I would be going in the direction away from the 0 facing direction, which would cause me to back up over here to -1. And that, again, is the point -1, 0 in Cartesian coordinates. So when you have an angle of 0, then actually the point in polar coordinates and Cartesian coordinates have the exact same coordinates. Now, however, the thing, one of the things to begin to recognize, back like you did in trig, is that when angles are involved, when you go past 2 pi, you start to get the exact same angular measurement with a different number. So that was not explained very well. So let's consider the point 1, 0 that we started with. So what I'm going to point out to you is that this could also be written with an r value of 1 and an angle of 2 pi. So one of the last points that I gave you that had a very high angle value, you can start to recognize that you have to just circle around enough times to find the right place to stop. And so what we'll start to see is that you can express the same point in polar coordinates many different ways. By adding 2 pi to the angle of a given polar coordinate point, you will get different coordinates because you added 2 pi, you changed the angle, but you'll end up landing on the exact same point. And so this sort of brings up a property of polar coordinates that that if I have the point r comma theta, that is equal to the point r comma theta plus 2k pi. So what that means is that that by adding any 2k multiple of pi to theta, you'll always get the exact same point because you end up pointing in the exact same direction. If you have the same r value, nothing has changed. So similarly, if I'm at a particular angle like 0 and I add an odd multiple of pi, so if I add pi, for example, then if I, instead of being at 0, I might be at pi, well, then I'll be facing in the opposite direction, but I can still get back to the point I started with by using the opposite r value. So -1 and pi for r also gives me this point and is equivalent to all the points on the right, as does, it's not smooth, as does -1 and 3 pi, because I added 2 pi to the previous point, which will give me the same point. So that means that if I have an original point, it is also equivalent to all formats of the point in which I have added an odd multiple of pi to where I started with and changed the sign of my r value to be the opposite. So that means r theta is also equal to all points of the form with the opposite r value and with theta added to some odd value of pi, which we can write as 2k plus 1 times pi. So here we have added even multiple of pi, and here we added odd multiple of pi. And have opposite r, meaning the opposite sign r value. So this is very, very different in polar than it is in Cartesian coordinates. In Cartesian coordinates, if you change either the x number or the y number in any way, you get a different point. There is one and only one way to express the coordinates of a particular point in Cartesian coordinates. Whereas in polar coordinates, every point can be expressed infinitely many different ways. Questions, comments, discussions about that idea? All right, so let's try a couple of short examples right off of that concept to see if it makes sense to folks. So in this time, what I'm going to do is I'm going to put up a couple of problems, and then let's try breaking the class into a couple of different groups, because these problems will have lots of different possible right answers. So I'd like you guys to try to check your answers with each other and see if you agree that they're valid. Let's see if this works. Again, we're trying to give this a try. So here's a statement of the problem. Find 4 different ways to express this is the polar points, 2 pi over 2 with other polar coordinates. So it's pretty easy to just generate from a point different ways to write that point. But more importantly, it's important to realize that if you have 2 different polar coordinate points, that you might actually be talking about the same point. And that's just something to keep in mind. And what we saw in when I was going through examples of making polar graphs in the videos is that you can go through angle values and then reach a point where the graph just starts to retrace itself. And of course, that never happens in a Cartesian coordinate graph, because every time you change x, you get a different point, whether you got the same y value or not. But in polar, every time you change the angle, you may get a point that you already graphed before, and that's sort of why graphs can sort of redraw on themselves in later angles and things like that. Okay, so let's refresh. All right, so now let's get more to the nitty-gritty of things a little bit. So once you're working and warmed up with the idea of points, you want to then get to a stage where you can try to actually make polar graphs. And this is where things can get interesting and take time and practice. And so polar graphs, again, like with Cartesian graphs, is going to be when you have points on a polar graphing system that are solutions to an equation in the variables. And so let's just give you guys a chance to try to maybe make a simple graph or two. Or ask questions about it. So let's say we had, this is one of the sort of key starting quintessential examples. So let's say we had the r, and again, usually you have r as a function of theta, where you plug in for theta and you see what you get for r. So let's say we have that r of theta is equal to 4 times sine of 2 theta. So if you use like a TI calculator, you can get polar graphs on pretty much all the Texas Instrument main calculators. But in the beginning, to understand polar graphs well, the thing to do is to make them yourself. Plot points, connect dots, try to see patterns, things like that. So let's take a few minutes to see if you could explore trying to create the graph of all the points that satisfy this polar equation. And chime out or speak out if you have questions. At some point, it might be if you are able to create a graph on a screen in some way and you're able to share that, that might be a way you could show people what you got, and then we could see if people got the same graphs. Let's explore this together and see if we can figure out what to do and how to make the correct graph. So one way we might segue into this graph if students are working on it, and it usually does take a while to orient yourself to the idea of polar graphing, is it also could be that instead of sharing a whole graph, students might share some points that they got in Cartesian format, in polar coordinates that satisfy the equation. But up to you guys. Trying to find ways that we can all interact over these problems and learn from each other and also get some practice to better our understanding. So feel free to chime in if you want to share some points you got or a graph that you got, or if you have any questions.
So, Professor, you said we can look at these type of problems in the Cartesian coordinate system. Like we can draw out the sine function.
Yes. So it's not that you look at the points in the Cartesian system. If I graph, like with r being the y value and theta being the x value, and if I just graph 4 sine of 2 theta, then what I'm seeing in a little Cartesian graph is as the angle changes, what is r doing? I'm sort of looking at the relationship between the two in the typical way that we're used to looking at it. But then I can translate that into what that would mean about the graph. So for example, in that format, when the sine value goes up and you get to the top of the sine bump, that during the angular range where that happened, that's where the r value also went out away from the origin. So the book maps that out because that is very typically how people think about and make polar graphs themselves and understand how polar graphs work. Is they kind of think about the angle changing over time, or as the angle is increasing, how far away am I from the origin? Where of course in a polar graph, that angle is sweeping out in a counterclockwise direction. And that's a little harder to feel intuitive about. So that's the method described in the book and in some of my my video explanations to try to somehow make the graph and see the pattern. Does that answer your question?
Yeah, so it kind of helps us like look at the r value as that sine graph goes on.
Imagining that you're standing at the origin and you're rotating your perspective counterclockwise and you're looking across these angles. And then as you're looking out, you're imagining sort of how far you would go away from the origin in that direction to get to points which make the graph. Well, that's kind of hard to visualize, but if you instead think about the angle being written out from left to right and look at the sine function, it might be easier. So it's a method. It's not a requirement, but it's a way to try to eventually get to the point where you're not just plotting points and connecting dots, but that you're instead perhaps plotting key points and then connecting those dots together by imagining, well, the r value would go from 0 up to 4 during this angular range. Well, if you write that out from left to right, you can see that, but then to graph it, you have to sort of sweep out that angular range counterclockwise on the graph and then have the curve swing out away from the origin and then maybe come back. That's why we get leaves and things like that.
Sounds good.
Yeah, so theta is the what's called the input variable, or the independent variable. It's different names for it, but basically it's like what we normally would think of for x, where you start with x and you see what you get for y. So in this case, you start with theta and see what you get for r. And that's why we write r of theta, to sort of say the answer for r is a function of theta you plug into to see what you get. Does that make sense?
Yeah.
And
So
you can,
like, for example, I
table
put
of
in
values
pi
or
over 4,
pi over 4,
and that would give me 4. And so pi over 4 would be between 0 and pi over 2. And then you would go out 4.
Right, so pi over 4 is like at a 45-degree angle.
Mhm.
And so if you can see the system I have on the screen, so then you would identify which one is pi over 4. So here's 0. Whoops. Yeah, there we go. Here's 0. This is pi over 6. This is pi over 3. And up here is pi over 4. And as we expect, that's at a 45-degree angle. So then I would go start from the origin and go up along that angular direction. 1, 2, 3, 4. And then there would be my point.
Okay, that makes sense.
Yeah, and then you can also make a little table of values where you put in your thetas and your r's, and then you get several points, and then you can connect the dots, if that makes sense. And so you could say, oh, well, when I was out here at pi over 4 for theta, I got a 4 for r, as an example. And then you can plug in a 0, pi over 2, various theta values. Oh, that looks terrible. Let's just erase it. And then, yeah, so that's the best way to start to understand polar graphs, is literally one point at a time, connect the dots, just like you did when you first started to make Cartesian graphs.
Okay, that's what I did, and I got like a clover kind of shape.
Nice. And how many leaves on your clover?
4.
Very nice. Okay. And so this is a good example, because you can see what a typical polar graph looks like compared to a Cartesian graph. The fact that you have stuff sort of with symmetry around the origin, often that you have parts of the graph that after a while just start retracing themselves if your function is periodic and things like that. And you have to kind of go through examples of these types of graphs. And the book even goes so far as to start to name some of these with names that have been used, like a cartoid and things like that. You know, I'm not very interested or think it's worth a lot of time to spend on the vocabulary that will develop if you ended up working with these a lot. Or not. We're going to work with this for just a couple sections. But, you know, saying, hey, I got like a 4-leaf clover is a perfect descriptive way to get a sense of what the kind of graphs look like when you're using polar to make graphs.
Okay.
Okay, that's a good query. So I think we can kind of think of it like with Cartesian graphs, that normally if you have an expression as a function of x, you end up getting into the habit of choosing values of x that you think will make it easier to evaluate the expression. So for example, if you're graphing the square root of x, then you would probably choose x values to plug in that were perfect squares, so that they would come out to be nice points that you could graph. So when you have a theta, usually, not always, but it's quite often that theta will be inside of a trig function, sine or cosine or something. It doesn't have to be, but it's very common. And in general, we've been trained with angles that the common angles we're used to working with are some sort of fractional portion of pi. So pi, multiples of pi, pi over 2, pi over 3, pi over 6. And those are the ones that we are usually able to evaluate in a trig function without having to get some decimal version on a calculator because of the primary common trig results on those angles. And using SOHCAHTOA and things like that for remembrances of what, for example, sine of pi over 3 might be, or something like that. In any event, so you usually would probably choose theta values to make your table of values, so that if you plug them into sine of 2 theta, you can get an answer for that without having to, you know, look at your trig card or something like that. And the truth is that you don't need a lot of those to do that. So for example, in this problem, if I was trying to imagine making a table of values and plugging in some theta values to figure out what I would get for R, well, almost always the first thing we're just going to try is plugging in a 0, which is the same thing we do if we have X and Y coordinates. And sine of 0 is 0. And so that means R would be 0. And so we know our graph starts at the origin. And then let's say I went all the way up to the point that Sierra suggested, which is that if I plug in pi over 4, then I'm looking at sine of 2 times pi over 4, which means I'm looking at sine of pi over 2. So as I'm imagining that nice value, because we know that pi over 2 is where the sine hits the top of its bump in its little wave cycle. And so that sine of pi over 2 is a 1, and then this would come out to be 4. So we already concluded, and that point is already plotted on my graph here. Now, what Parjit was talking about is that the way you translate these 2 points that we just got into a graph connecting the 2 points, instead of just like drawing a straight line between the two, that would not be correct here. We envision a graph of the function 4 times sine of 2 theta in a Cartesian system, where I'm imagining going up to 4 and going down to minus 4. And that as I go out to pi, the function goes up, down, and back up. And so that when I'm at pi over 4, I'm at the top, which is at 4. I started at 0. Then when I get to pi over 2, I'll be back to 0. When I get to 3 pi over 4, I'll be down here at negative 4. And when I get all the way to pi, I'll be at 0 again. So if I'm imagining that graph just from left to right, then I can think more comfortably about how to transition between these 2 points that I got down here. Well, actually, let's do this. So if I think of this as point number 1, and I think of this as point number 2, then on my graph, here's point number 1, and out here is point number 2. But the question is, how do I get from 1 to 2? It used to be we just kept thinking about left to right, that I'd say, okay, somehow I go from there to there. But that's not what we want to do in polar, because in polar, the way I got from point 1 to point 2 is that I was initially facing at the angle of 0, and then I finished facing at this angle here, and that what changed is that the angle rotated from angle 0 to angle pi over 4. And so that as this point went, as point 1 went to point 2, it's because the R value increased from 0 to 4 as the angle changed in that direction. So that means initially I was pointing at 0 and I left the origin as I was pointing at 0, but as I left the origin, I also started to move up to an angle of pi over 4. So that means I come out this way, and then as I'm rotating counterclockwise, I end up with that R value. And that gives us sort of the idea of how we connect the dots in a polar graph so that I get this arc here. And so the way I see that is I can think over on a left to right version, that as I went from 0 to pi over 4, the R value went up and up and up until it got to 4. And what that translates to in the polar graph is that the R value is going out further and further and further away from the origin as I sketch out here. And that's how I end up with the graph that I end up with. Then if I'm starting to get that dynamic, then you could say, okay, well then as I sweep out the next range from pi over 4 to pi over 2, and I start to turn in that direction, what does the R value do? It goes from 4 back down to 0. which means that the distance away from the origin will go from its peak at 4 and shrink back down to 0 in the same way that it went out to 4, since the sine function is symmetric. And then that allows me to connect the dots for the next phase, where this then sweeps back down to the origin. And that's how we get this leaf of the flower. As Sierra pointed out, you get kind of a 4-leaf flower. So that's the idea about choosing theta values that you can plug into the function to get nice answers, to then give you polar points to plot. But then how to connect those points together with a graph with all the intermediary points without trying to plot dozens and dozens of little change points. That's where the book's description and what I just tried to describe of sort of imagining what the 4 sine 2 theta function looks like from left to right, and then convert that into angular changes on a polar graph and points going away from the origin and maybe coming back to the origin, things like that. So is that helpful to get an idea for those who are trying to navigate this process? Is there follow-up questions to this to try to make sense of it?
That helps clear things up.
It definitely takes some trial and error and playing with things. And you have to kind of look at it several times to just wrap your mind around. It's just so different than what we're used to. But you could do it. So then the next part of this graph, just to try to feel comfortable, is that now the R values are going down into negative territory as we go from pi over 2 to pi. So that means as I sweep out this part of the angle, which is looking into quadrant 2, that instead of going toward that quadrant, since the R values are negative, ending up with being at a -4 when we get to 3 pi over 4, that I have to instead back up into quadrant 4. So what would happen is that I would go out, and when I get to 3 pi over 4, I would be backing up 4 spaces, and I would end up at this point down here, which is when R is at -4 and the angle is at 3 pi over 4. And I need to get to that point as I go through these angles. So as I'm going, I'm starting here and I'm moving this way and going through these angles, but the points are coming out in the opposite direction and then ending up there, and then of course shrinking back down to 0 as you went to complete that. So this arc number 1 I got, or this leaf I should say, this leaf number 1 I got when I was going from 0 to pi over 2, then this would be leaf number 2 that I would get when I'm going from pi over 2 to pi. So while I'm over here in this angular range, I'm producing leaf number 2. And if you follow this through, then you'll get leaf number 3, and then you'll get leaf number 4, and you'll have this 4-leaf clover that Sierra referred to. Nice big mess. Questions, comments, discussion?
So just so I understood, when we're going through the points pi over 6, pi over 3, pi over 4, once we start going into the let's say 5 pi over 6, or yeah, like 5 pi over 6, we're actually drawing in the 4th quadrant.
Correct. And the reason the values between pi over 2 and pi, which normally would be angles facing into the 2nd quadrant. So when I'm over here between pi over 2 and pi, the reason we were drawing down here in the 4th quadrant is because the function for R produces negative numbers. And so when R is a negative number, you start looking this way, but because r is negative, you don't move in that direction. You move in the reverse of that direction. You back up.
Oh, okay, I see.
So if I'm looking over here, if that's the place I'm looking over into the second quadrant, and I'm starting at the origin, but r is -4, then I end up having to back up into the fourth quadrant 4 spaces, which causes my point to land in the fourth quadrant instead of in the second quadrant, because r is negative.
So in an abstract way, we can think of r as y.
No,
No? Okay.
because r could be directly left or right, just depending on what angle you're pointing at.
Okay. But so it'll always be like kind of like the opposite of what we're thinking.
Well, the way to think of it is that you're standing at the origin.
Mm-hmm.
Think of you as like standing on the top of the globe or something like that.
Okay.
And that the theta gives you the direction that you face before you decide to move. So you turn counterclockwise, pi over 2 or pi, you turn to a particular direction, you face that way.
Mm-hmm.
Then the r value tells you how far you have to walk. And if r value is positive, then you walk forward in the direction that you're facing.
Mm-hmm.
If r is negative, then you start walking backward away from the
Okay.
direction you're facing.
That's kind of what I was thinking. Okay, yeah.
Okay, so yeah, I don't think y or x have really anything to do with that, because it's y is always up and down and x is always left and right.
Right. I was just thinking of it was just an abstract way of thinking for me, but yeah. Okay.
Yeah, I mean, as long as your brain can get around it, a lot of times people make their own orientations that, that aren't what I've said, which is fine. And that's absolutely fantastic. And one of the ways might be to make the translation that you're talking about is that little left and right graph that,
Right.
if I graph the function, as I just described before, where this is theta and this is r, well, then when I'm graphing it that way, then yeah, r is y, because I've literally assigned the y-axis to be the r value and the x-axis to be the theta value. Of course, the points that I then see
Are different, right?
look nothing like the graph.
Yeah.
But that, as an intermediate thought process, is very helpful to understand the transition from point to point in the polar coordinate graph. And that's why the book emphasizes it, and I think it's a good thing to consider.
Okay, cool.